So what we're going to do today is we're going to talk about something called impulse, okay? Which is going to look at the connection between force, time, and momentum. Now I'm going to start with a really simple concept. How would you express the formula for momentum? How would you express that? No, just what's the formula for momentum? mv, right? P equals mv. Okay. How would you express change in momentum? It would be what? M delta v, right? Because if the momentum is changing, it's most likely going to be an example of a scenario where the speed is changing. Now, there could be an example where the mass is changing, like if it's a rocket that's flying through the air, the mass could change because as the rocket uses up fuel, its mass decreases. Okay? But the scenarios that we've been looking at, if there's a change in momentum, like if a ball hits another ball, its speed is changing, so there's a change in speed. And you know, you represent a change in anything with that little delta symbol, correct? Now, that means really what we have is a mass with a change in speed, correct? So if you look at the units, you have kilograms, kilograms, meters per second. Right? Now, if I look at the unit for force, force is MA. Correct? Now, you know the unit for force is a Newton, but the Newton actually represents a kilogram, meter per second squared. That's the unit of 1 Newton, right? It's a kilogram meter per second squared. Now, I want you to look at this unit, and I want you to look at this unit. And they look almost the same, right? You have kilogram, meter. In one case, it's per second, and the other case is per second squared. So my question to you is, how can I convert this unit into this unit? What could I multiply here to get this unit? The answer is just simply seconds. Right? This is telling us something. If we take force, which we know is kilogram meter per second squared, and we times it or multiply it by time in seconds, you get a change in momentum. Because if I apply a force, that will generate acceleration. For a certain amount of time, that will change the speed, which means you're changing the what? The momentum. So the formula for impulse is actually Ft equals m delta v. Okay? An impulse is a force applied for a given amount of time, which will result in a change in momentum. Now, the concept is really simple. I'm going to show you some really simple calculations with some real scenarios. Okay? What I'm going to show you first is an example of how do you calculate the force in baseball when someone hits a ball. Alright? Using this concept. Using this equation where impulse equals the change in momentum. Alright? So I'm going to show you a little clip. See what happens to baseball when it gets hit by a ball. By a bat. Hold on. So let's take a look. Hopefully this opens up. Alright, here we go. So this is in slow motion, alright? Slow motion. So you can see here, ball is coming. Now I want you to look at the speed of the ball. Obviously you know it's going to change. And then I want you to look at the speed of the bat. Okay? Take a look. You'll notice the bat vibrates. It does actually slow down a little bit. Obviously, the ball actually changes direction. Now, the speed of the ball will not be the same. That should be a little bit. Coming in at a particular speed, not baseball, because they're American, they like it in miles per hour. So if it's coming in at 90 miles per hour, it's probably going to leave at maybe 100 miles per hour. Okay? So there's obviously clearly a change in momentum here. And you'll notice that it's not maybe a perfectly elastic condition, because if I look at the moment of impact, you'll notice that some of the energy actually goes into, you might notice it's probably hard to see it on this video clip, the actual ball compresses a little bit, and the bat warps and bends a little bit. Some of the energy is lost, right? So the kinetic energy is not completely conserved. But we're not worrying about that. I'm not going to ask you to calculate anything with the kinetic energy. I'm just going to ask you to examine the force acting in this scenario. All right? And, sorry, hold on. Let me just pause this. We have a visitor. Zoom. Sorry. Actually, in this picture here, you can really see the decompression of the ball. But anyways, we're not really worrying about that. We're going to worry about the force of impact in a baseball swing. So you're going to need some numbers. So imagine that we have a ball. And here, by the way, is a neat picture. I don't know when this was taken. But you can clearly see here that there's some deformation going on the ball, right? So this is a person hitting a ball. So let's imagine we had some information. We have a ball that's approaching. We're going to use meters per second. Okay? And it's approaching with a speed. It says 40 meters per second, and it takes off in the other direction at 50 meters per second. And we have how long it takes. So the impact, how long the ball stays on the bat, is about 0.6 milliseconds. We want to know the force of impact. So the equation that we have is Ft equals m delta v, right? We're going to arrange this for force. So F is going to equal m delta v over t. So the mass of the ball is 0.15 kilograms. Now let's think about the speed, okay? So this is your VF. This is your VI, but they're opposite directions. So if we make this positive, then the initial must have been negative, right? This is very important. So if the 50 is positive, we know it's VF minus VI. The VI had to have been negative. Conversely, you could make the initial positive and the final negative. So it's m times the change in speed over the time in seconds. Now, 0.6 milliseconds would be 0.6 times 10 to the negative 3 seconds. All right? And you'll have your force. So, what is that? What is the value for that force? Let's work this out. So, 0.15 kilograms times the change in speed, which is 90, over 0.6 milliseconds. What is that force? It's a pretty big number. No, can't be. Did you divide by 0.6 milliseconds? It's 10 to the negative 3. The denominator is very tiny. So the number should be quite big. 90 times 0.15 is 9 times 0.1 is 9. So it's about 13. So the numerator is 13 and a half. Yeah. 22,500. No problem. 22,500. Now, if you watch Walking Dead, anybody here watch Walking Dead? You guys don't watch Walking Dead? You do, can? So, in the episode Walking Dead, there's a really bad character called Negan who uses a bat, and what he does is he crushes people's skull with it. I'm not going to describe that to you. It's pretty obvious what would happen if a baseball bat hit a skull. To fracture a skull, you need less than 1,000 newtons of force. So that amount of force would do some pretty devastating damage to a human being. So that's a lot of force, okay? The equation for impulse is quite simple, right? Not involving any trigonometry or anything that's pretty complicated. Let's look at another example, okay? We're going to do the same thing. We're going to, instead of looking at a ball, we're going to look at the force of impact for a car hitting a wall at 190 kilometers per hour. Okay? Now, I actually downloaded this video. So, why don't you, I guess you're writing down the question. So, do you want me to pause it? Okay, I'm going to pause it. Okay, so we're going to calculate the force of impact of a Ford Focus hitting a wall, a barrier, at 190 kilometers per hour. You said the mass of the Focus is about 1,600 kilograms? Okay, so we're going to start with putting in our data. So the mass of the Focus, we'll just say it's about 1,600 kilograms. Okay. Now we're going to convert this to meters per second. So remember, divide by 3.6. So what is that as an initial speed? What's 190 kilometers per hour as a speed in meters per second? 52 point. I'm just going to round out to 53. And obviously, if it crashes into a wall, the final speed will be what? 0. Now, what we don't know is how long this is going to take. But I'm going to show you the video clip. So let's watch the video clip, because I'll tell you how long it takes, okay? So here is a Ford Focus hitting a wall at 190 kilometers per hour. Watch this. They have some dummies in here.
This is different. Only the rear end escapes.
Wow, look at that.
And the passengers don't ask. Got the hairs on the back of my neck as sharp as nails.
Watch the impact.
The car decelerates from 120 miles an hour to 0 in 68 milliseconds.
No one's going to survive that.
400 G. The front end hits the wall with such force that the back end rises up 90 degrees and the car is slammed down onto its nose. Crash test expert Tony Payne talks me through the scale of this wreckage. Absolutely mauled. Yes, you've got the vehicle crushing all the way back to the vehicle. You can see here, for an occupant in there, absolutely no survival space at all. There's the rear seat, and there's the steering wheel there, and literally it's been compressed between the front and rear seat down for that thing. Goodness me. It's almost turned into a piece of modern art. You can go right round into the car itself. Once it's right in there, that's instrumentation pump, and the person's literally in that area. I mean, I know it's all not real, but that's the almighty haunting. It is an extreme scenario, but modern family hatchbacks can reach the speeds we saw today. Maybe it'll make you think twice the next time you want to put your foot down.
Okay, that's pretty scary. What did they say was the speed? No, the impact time was 68 milliseconds. Okay, so 68 milliseconds, which is 68 times 10 to the minus 3 seconds. Okay, so let's work out this force of impact on the Ford Focus. Miles per hour, yeah. So I had it at 190 kilometers per hour. Again, our American friends like miles per hour. So again, it's m delta v over t, 1600. Now, delta v will be 53, right? Because it's 53 and 0. So the difference will be 53 over 68 milliseconds. So what is our force of impact? Now keep in mind that about 500 newtons is enough to crush a skull, fracture a human skull. $1 million. Also, it's 1 million. Okay, say that again. 1.2 million? Okay, that's okay. You got 12 million? Is there 12 million? So you got 1.2 times 10 to the 7 newtons? 1.2 million. Are you guys okay? You guys don't know. So it's 1.2 million. So it's 1.2 times 10 to the 6 newtons. Alright. So it's 1.2 million. Wow. That's a lot of force. If you think about the weight of an elephant, we compare this to the weight of an elephant, right? How much does an elephant weigh? I mean, let's have some context here. Okay, 1.2 million newtons. All right, so what? What does an elephant weigh? What's the mass of an elephant? How much is what's the mass of an elephant? Is it 2 kilograms? I mean, sorry, 2,000 kilograms? Who wants to look it up? Mass of an elephant. I'm 100, not quite 100 kilograms. So, very funny. An elephant is 5,000 kilograms? Wow. 5,000 how many? But what's the weight of it? So, let's go with the biggest elephant. 6,000 kilograms times 9.8. You know, if you want to know the weight, it's times G, right? So, what is that? Well, close to 60,000? How many times greater, or how many elephants would need to step on you to be equivalent to the force of impact of that barrier stopping the focus? Is it 20? Yeah, so you imagine 20 elephant. You'd be squat. And you saw in the video what happened, right? The rear seat and the steering wheel were what? Like a foot apart from each other? Like you would be obliterated. Just obliterated. Anyways, that's it for impulse. Easy? What do you think? Easy? Probably one of the easiest topics you'll learn. So let's stop there. But I do want to show you some other stuff. So let's end here, okay?